This was work I did on my sabbatical, trying to find out what it's like to be a grad student. So I would go to David Shea's office, and every week I'd have to make sure we had something to talk about. Turned out that's very easy with David. So I also want to thank Zhang Li, who I had a lot of discussions with about this work of all of the web. So the talk title is kind of a boring title, but you need all of those words to differentiate the problem from other problems. To motivate why a boring title is interesting, it's we might do this. If you think about sort of wireless network physical layer research, there's sort of 3 channel state models that are commonly employed. One is the AWGN fixed channels. The S and R's are known, and they're fixed on wireless links. The other model is fading, where the channel state, the fading, is known both at the receiver and at the transmitter. And the third is that the fading state is known at the receiver, but not at the transmitter. So this is consistent with you send packets that have pilot tones in them. The receiver is able to use those pilot tones to form very accurate channel state estimates, but you don't posit that there's a feedback loop that provides the same channel state information in a timely way to the transmitter. So those are the sort of the 3 most important models for channel state. And in these models, you can look at the MAC channel, many to one communication, fundamental for each channel state model. And you might look at the broadcast channel. Right? One transmitter, like a cellular base station, trying to deliver independent messages to multiple receivers. And so now we can have a short quiz, right? And the quiz is like Sesame Street. It's like one of these things is not like the others. So we have 6 boxes. One of them is different. So some of you, I think Rohan has been at this talk. You've been at this talk before. You're being polite, not answering. So I'll tell you the answer. The answer is the broadcast channel, where there's fading and the channel state is only known at the receivers, is the only network for which of these 6, for which the capacity region is unknown. The other 5 are solved. So.
May I ask a question? So in practical systems where you would think you are in the red text box, however, with a simple trick of just 1 bit of NAC or ACK, the transmitter can start with the aggressive rate and then keep on sending additional redundancy to the point where the packet gets decoded. Would that be a hybrid? Because there is feedback by virtue of sending the bit that didn't quite got the packet yet. So the rate is adjusting to the receiver conditions, but without full explicit knowledge of the transmitter.
So I would say that's a situation with feedback.
Okay.
Which
Fair enough.
We don't assume any feedback here.
Fair enough.
But okay, so let's sort of dig into this and go back to sort of the basics. I wasn't sure who was going to attend the talk, so I have about 8 or 9 slides that are kind of introductory material that I might skip, but I'll try to go through them quickly, just fast enough that if you're new to this subject, this will be slightly incomprehensible. So the 2-user broadcast channel, this is an example of that, right? A special case. Formulated by Cover at 72, we have 2 messages, W1, W2. We have a transmitter who puts out a signal X. Receiver 1 gets signal Y1 to a channel Y1 given X. Receiver 2 gets Y2. The receiver 1 tries its best to decode W1, and receiver 2 tries the same for W2. So I think I just said all of these bullets. And the key question is, what kind of reliable communication rates R1 and R2 are possible for the pair of users? So when you formulate that, you realize that, capacity isn't a number in this situation, it's a region of pairs of values R1 and R2. One sort of easy operating point is you devote all your resources to communicating with receiver 1, and you achieve Shannon capacity for user 1. That's one operating point. A second operating point is Shannon capacity for user 2. You design the optimal signaling strategy for the user 2 channel. Don't communicate anything. So, of course, time sharing enables you to get all points along this line, and mixing that with maybe doing nothing gives you all points in the triangular region. So Kober had an insight in 72, which is that you can do better than time sharing. And you can particularly, like in this example, where the capacity of the channel to receiver 1 is higher than that for receiver 2, you can exploit this better channel. And his idea was to transmit to both users simultaneously using a superposition, an X, which is a signal V1 for user 1 plus V2 for user 2. So he showed that this allows you to achieve points that has kind of a bulge over this capacity region for time sharing. Okay, so the idea of this superposition coding, which is, I'm including these slides because I have to work very hard to make these simple pictures. So you have this code word superposition, code word V2 for user 2 and V1 for user 1. And the way to view this is that for each code word V2, there's kind of a cloud of code words for V1 around that V2. So you think about a signal for V2, and now all the different V1s is this cloud. And similarly, here's another V2 and another cloud of signals V1 that convey messages to user 1. And you keep doing this, and you fill up the signal space with these clouds. And when you go to do decoding, receiver 2, who has this sort of inferior, less good channel, all he's able to do is identify that the transmitted signal is in one of those clouds, right? And he can resolve essentially log of the number of clouds, how many bits in one. Receiver 1, on the other hand, he has maybe a higher SNR signal, a better channel, and he can look inside the cloud and see the individual points and resolve which point was communicated within the cloud. Maybe this one or that one. And so he looks inside and he can resolve messages that are like resolving which message is in the cloud. So that's the idea of superposition coding, and you analyze this in particular channels. You get curves that bulge out, and it exploits the fact that the two channels are different, and that really that receiver 1 is better. So up near the point where user 2 is near capacity, you get kind of a horizontal bulge where a small reduction in rate for user 2 gives you a big gain for user 1. If somehow user 1 and user 2 have identical channels, the two channels are equal, in fact, you can't do any better. The bulge goes away. You get time sharing. And so the key idea here is this idea of a degraded channel that user 1, think about that superposition. He first does the user 2 job. He decodes his message, and then he goes on to look inside the cloud. He finds out which cloud, and so he can do anything user 2 can do, and then he can do something more.
Now, is this? Can you look at this as a dual of this successive input transmission?
In the space of high-dimensional coded vectors, yeah, you can think of it as being almost the same thing, right? But you want to say be cautionary because it's really over coded vectors, not over just low-dimensional signals. Okay, so I think I said this. So this idea of degraded channel is that we can represent the communication system in such a way that the input X goes to a channel to create the output for user 1, and then there is some mathematical or physical construction of a channel you pass the receiver 1 signal to create that for user 2, right? And the result is that receiver 1, he could have the receiver do this second processing on his own and create equivalent user 2 signals, so he can do anything that he can decode anything user 2 can decode. And there's some technical details that involving whether that's a real channel or whether it's a fake channel that provides the same marginals. I guess I'm going into it even though I wasn't going to. The key thing in this broadcast channel is that the actual capacity only depends on the marginal channels, X to Y1 and X to Y2, and doesn't depend on the joint channel. So what you need in this degradation is to have this kind of channel to user 2 be a mathematical construct that provides the right marginals. So if that didn't make sense, don't worry about it. So, okay, so for this degraded broadcast channel, capacity is actually known. So in general, the capacity region of the broadcast channel is unknown, but various special cases are known, and this is the most important special case. It's the case that Y2 is a degraded version of Y1, and here's the capacity region for discrete memberless channels found by Gallagher in '74, and also found by Bergmans for the Gaussian channel in '74, using a different proof technique. So if you're good at information theory or not, here's the idea. This signal V is a common message, right? It's a signal for user 2 that's decoded by both users. So the rate for user 2 is limited by the mutual information between V, the common message, and the receiver output for user 2, Y2. And on the other hand, user 1, he can decode that V, right? And his rate is then limited by the conditional mutual information between the input and Y1 given that V, which essentially says it's the residual information carried in the signal X, right, for receiver 1 after he learns what the message is from user 2. So that's the capacity region. It's fairly clear. Right, so a couple of comments. Culver superposition achieves capacity for degraded broadcast. Key idea is receiver 1 can decode anything receiver 2 can. This V encodes the message for receiver 2. Right? I think I said all of this. The better channel, receiver 1 also decodes V, strips that signal, and then decodes his own message. All right, so here's the history of the channel. Culver proposed superposition coding and I think invented the idea of the broadcast channel. Then there were a few years of sort of really active work. Bergmans found achievable rates and then the converse for the AWGN broadcast channel. Gallagher found the general degraded broadcast channel converse. Martin wrote papers that had kind of the most valuable inner and outer bounds. And in some cases, those bounds are the same and found capacity. And then between 1975 and 80, where a variety of special cases were solved. And then involving conditions on the channel, then kind of nothing happened for 2 decades. Like they couldn't solve the general problem. They're like, let's move on to something else. And then with the advent of wireless, people got really interested in this problem again because it was the physical representation of a base station communicating to wireless terminals. And real progress was made. Particularly, the most notable was the Gaussian vector broadcast channel, where you transmit through multiple antennas to receivers with multiple antennas, was solved in 2006 by Weingarten, Steinberg, and Shimon. So now let's get back to our problem. That kind of is the introduction of the talk. Which is 15 minutes. It's too long. So here's our problem in the fading channel. Signal X, receiver Y1 gets a fading gain, a phase times X plus a Gaussian noise. Receiver 2 gets the same thing, but with a different fading gain, random variable S2. We make the noises Z1 and Z2 unit power processes. this SI, if you think of SI as the fading gain for channel I, SI of t is in fact a time-varying channel state, and we're going to assume that it's an IID process, that you get a different fading gain with each symbol, IID. So in fact, in memory, maybe you could have exploited it, but this is sort of the fundamental case where you really have no clue of each instant of the channel state. So then we construct long code words, and each code word, right, each symbol of the code word sees an independent channel state. In fact, you see the full ergodic variation of the channel using long code words. And so our model is an ergodic capacity. So for the channel state, receiver I, he knows his fading gain, he knows his phase angle perfectly. In fact, maybe he estimates them, but the model is that he knows them perfectly. The transmitter knows
So
that.
the fading state changes symbol by symbol?
Yeah, of course. Yeah. So then you look at that, and there's sort of an information theoretic model where in the information theoretic model, what you do is that you label the SI and the theta I as outputs of the receiver. They're observations, and the full observation is the fading state, the phase, and the YI. And then you realize, well, the receiver I, you can do post-rotation of the signal to eliminate the phase. And when you do that, you can now just look at the I or the Q channel, right, and look at this real value channel where the observation now is Y1, which is just the channel gain times this real valued X plus noise, and you observe the YI and the channel state SI at receiver I. And for this is the model we'll analyze. Later we'll do some numerical things where we assume there's an I and Q and all the rates are double what these rates are. So capacity region of this is unknown, and kind of Tuninetti and Shamai worked on this in 2003, had some inner and outer bounds, and people sort of stopped working on this. So here's the rest of the talk. We have a model for this channel, which is built on a deterministic channel model. It's a fading channel built on instances of a deterministic channel. And for this model, we will find the capacity, propose an achievability scheme that involves a kind of a greedy assignment, an outer bound based on channel enhancement. We'll show they're the same. And then, so this model of the layered erasure broadcast channel it's academically nice in the sense that in the sort of the canon of all the solved broadcast channel problems, it is a broadcast channel where we find the capacity and it doesn't meet the conditions of all the other known broadcast channels that have been solved. Right? But on the other hand, it's kind of a fictional model, right? And it doesn't represent a real physical channel, so it's kind of a intellectual curiosity as opposed to being useful. So to sort of do something more useful, we then try to apply the ideas of this layered erasure broadcast channel to the channel we really care about, the AWGN channel. And then in that channel, we'll essentially do the same things as we did for layered erasure, and we'll get some inner and outer bounds, and we'll get some comparisons to how close to their capacity. All right, so this layered erasure channel is built on the idea of a binary expansion deterministic channel that was proposed by Vestager, Javi, and Shea, and pretty much since 2007, if you hang around with David, you work on problems that say, well, let's take this idea and try it in new places and see what kind of insight we get. So that's sort of the genesis of this work. So the model is this, that you think about the signal x, which is a real value number, and you think about it as a kind of a binary expansion, x1, x2, x3. When you think of it that way, x2 is a signal that's 6 dB weaker than X1 because it's the next digit in binary expansion. So you think about transmitting this binary expansion, and the receiver, when he receives this X, it's kind of a toy model, but what happens is that he'll receive some of these bits clearly, but in fact, like somewhere down in the depths of the binary expansion, the bits will be corrupted by noise. So for instance, you think of this as the noise level, and the first bit is received with a channel gain that's down either 3 dB or 6 dB. It appears as Y2, but this is deterministic. Y2 is exactly X1, and Y3 is exactly X2. Right? And in this case, you receive X1 to X4 perfectly, and the noise washes out with this 5, the fifth bit in the binary expansion. So here in the first example of this channel, you receive 4 bits. Here in the next example, the noise is worse, right? I'm sorry, the channel gain is worse, right? So X1 now appears 3 levels down at Y4, and you only receive 2 bits, and these bits are lost in the noise. Right?
So this is very interesting, but it's very accessible. But if I try to relate it to previous knowledge, even in the noise level, if I have a Shannon view and I wait for long enough, I can always get 1 bit over, 1 extra bit over. It's just going to be
yeah. So it's kind of
so is this sort of, you're assuming a per channel use normalization behind this?
So really, it's a high SNR kind of a model, right? Because the model kind of breaks down in the sense that, oh, you're right. In a true AWGN channel, you can have very low SNR, right? And you transmit enough symbols.
There's always a non-zero capacity, whatever it is.
Right. So in here, in this model, right, there's some moment where the SNR is bad enough you don't get 1 bit. So the genesis of this approximation is that you want to use it in high SNR situations where in high SNR, right, you get several bits. You get a clear observation of a with very little noise, and you resolve a lot of information with symbol. So here's an extreme case where, the channel's quite bad, you don't get any bits.
So, Roy, is it like multi-level BPSK? So you have, for each of your modulation levels, you have only 2 levels, but you have many of them of different amplitude, which correspond to the 2 to the power n, which n is just a position of your digits. So you just sum them up.
In fact, when we get to our achievability scheme, you'll see exactly that idea in the signaling scheme we use for achievability. But we haven't gotten there yet. So the answer is yes. Okay, so here's a fading channel built on this idea. Right? The fading channel is that transmitter sends some binary expansion of up to Q bits, right? And the receiver, depending on the SNR of the channel, he receives some number n of those, and n is a random variable. So n is non-negative. It's between 0 and Q. And if n is high, right, it corresponds to having high SNR. If n is small, right, it's low SNR. And the what's happening is that the fading is erasing bits n plus 1 through Q, and the statistics of the channel fading process are given by the statistics of this PMF for random variable n. And in fast fading, N of t is an IID symbol-to-symbol process that each time we transmit this collection x1 to xq, you get some random number of the most significant n bits. Okay. So now you take that same idea and you extend it to a broadcast channel where now each receiver has a layered erasure channel. Y1, receiver 1 gets N1 bits, and receiver 2 gets N2 bits, and N1 and N2 may have different distributions. So the broadcast channel is really defined by these distributions. And depending on the PMFs for N1 and 2, the channel may or may not be degraded, or may not be any of the other sort of known cases of broadcast channel for which we know the capacity. So, and it's also, you don't have a parallel channel here, so parallel broadcast channels are well understood because the erasures are dependent. If bit at level 5 is erased, then all lower, say less significant, 6, 7, 8 are also erased. And so capacity of this channel wasn't known, but it turns out capacity is pretty simple. So if you want to find the capacity, which really is a capacity region, you want to find this kind of curving, bulgy surface. Find all the points, and the approach to doing that is to formulate kind of a weighted sum rate maximization. So you assume that you want to solve for the maximum R1 plus omega R2, which is some rate you assign, a weight you assign to the rate for user 2. And so geometrically what that means is you form this vector 1 omega, right? And the maximization of this is you find a point on the plane perpendicular to this vector that just touches the surface, right? And that gives you two things, right? It gives you an outer bound on this sum rate, but this plane also defines for a constraint on the whole region. And if you then take the intersection of all such constraints, you would get an outer bound region. Conversely, if you're doing some kind of achievability scheme, you could find a set of achievable region. The outer bound is more important. So here's an achievability scheme that we kind of make up off the top of our head, right? No, that's a lie. So the lie is we first did a converse, right? And then realized, like, oh, this converse says this is what the answer is, right? And realize that, oh, you can get it very simply. So here's the thing, right? You can take the bit at level n, right, for this layered erasure channel, and you could transmit it to and say it's for user 1 or for user 2. So who should you assign it to? So when you think about this weighted sum rate reward, right? If you assign bit n to receiver I, he receives it perfectly if his channel state is greater than or equal to n, and otherwise he gets 0. Right? So the weighted sum rate, the reward is just simply the probability if you assign it to receiver 1 that receiver 1 receives it, which is just the probability n1 is greater than or equal to n. So it's this complementary CDS evaluated with n. If you send the bit to receiver 2, the weighted sum rate reward it's the same, but there's this weight factor omega because bits assigned to receiver 2 have value omega, not just 1. Right? So the greedy, easy thing to do is to look at this bit and say, I should assign it to the person who gives me the better reward. Right? So that's greedy bit assignment, right? If the reward for user 1 is better than the reward for user 2, I assign it to user 1, and otherwise do the opposite. So you do that, and the claim is that achieves capacity for this channel. So to prove it achieves capacity, you have to have a converse, and the converse uses essentially the technique that all known non-degraded broadcast channels use to find capacity, which is a technique known as channel enhancement. So the idea of channel enhancement is that for omega bigger than 1, we have a preference for the bits of user 2. Right? You get more value for his bits. So what we do is we enhance the channel for receiver 1. We create a fake channel for receiver 1 that's better than his real channel, which can only increase the set of achievable rates. Right? But we do it in such a way that we do accomplish two things. Right? We create a degraded channel, right? But in fact, right, we never actually transmit, we never in fact let channel user 1 have the benefit of that channel enhancement. In fact, the bits that are enhanced all go to the other guy. So maybe that sounds a little goofy. So here's what we do. If the complementary CDF at level n for receiver 1 is better than the weighted one for receiver 2, these are bits we're assigning to receiver 1, we do nothing. Right? We leave the complementary CDF for the enhanced channel to be the same in that state. And on the other hand, if the complementary CDF, the reward you get at level n for receiver 1 is less than the reward for receiver 2. Now we enhance his channel, we create a new channel, right, which is better, right? It's better either we make it perfect or, right, we make it equal, we make his probability of decoding equal to the reward we get for sending it to the other guy. So this number here might be bigger than 1, and if it is, then we simply make the coding for the enhanced channel for receiver 1 perfect.
If you have one bit and you want to assign to either user 1 or user 2, is that the problem?
No, so in the achievability scheme, right, we describe the problem as assigning the bits to the different users, right? But that was kind of an ad hoc thing he did, right? There's nothing about, we don't know if that achieves capacity or not. So when you do an outer bound, you can't assume that, oh, you're going to assign the bits, right? You just have a channel, right? The channel has a certain probabilistic characterization, right? And you can't make any assumptions about how you're going to transmit or how if you're going to assign bits or do anything like that. So the technique is to take the existing channel as they're handed to you, do this enhancement for user 1, right? That gives him a better channel than he truly has, which can only increase the set of possible rates, right? But we do it in such a way that we create a degraded channel. And when we do that, we're able to use the known results or capacity of the degraded channel to say, well, for this enhanced channel, this is the capacity region. And then we analyze that and show that we didn't, that it's exactly the same as our achievability.
But by keeping the complementary CDF the same, you didn't enhance the channel really.
Huh?
You kept it in the previous slide, you didn't. You kept the complementary CDF same.
No. So here's an example, right? So we'll do a simple example. We'll make the weight be the same, keep it simple. So receiver 1, right? He has a PMF, which is this is a complementary CDF. So with its N1 is greater than or equal to 0 with probability 1, and it's greater than or equal to 1 with probability 3/4. But on the other hand, it's greater than or equal to 2 with probability 0. So in this example, receiver 1 gets the first bit with probability 3/4 and never gets bit 2. And here, receiver 2, he gets the first bit with probability 1/2 and the second bit with probability 1/2, which means with probability 1/2 he gets 2 bits or he gets nothing. Right? So the two channels are different. Right? So what the enhancement does is it gives this a new receiver 1 gets a 1/2 probability of decoding the second bit. So this is then, we started with that physical channel. Now we're going to find a capacity region of this enhanced channel. And because this complementary CDF dominates that one, we have a degraded channel situation.
I agree, but there is the first implication that complementary PMF of N1 tilde
Yeah.
same as complementary CDF.
Yeah, but only for levels where user 1 was better than user 2, offered a bigger reward in the first place. So then we just didn't monkey around with.
So if omega is 1, it is never, the channel is never enhanced.
Huh?
If omega is 1,
No. So this is an example here where omega was 1, right? And we enhanced the channel by giving user 1 a look at bit number 2. And maybe, for instance, if omega had been 1.2, right? We would have made this number not half here, we would have made it 0.6, 1.2 times half. Okay, so
What if you had with N1 and N2 itself a degraded channel? If you had it.
oh, then I would be able to just say, oh, the capacity region is this, and blah, blah, blah. And
Oh, because it's already solved.
yeah, it's already, you don't do any enhancement, just leave it alone. Okay, so this is a degraded channel. Degraded channel, we know the capacity region. It's the mutual information. R1 gets this rate. It's just an expression we had before with the inputs and outputs we have, right? And then you take that constraint and you go to solve this weighted sum rate problem, and you solve it over the choice of auxiliary V and channel input X. And some joint distribution of those. And at this point where you take this expression, you plug in these two outer bounds for R1 and R2, and then you do a bunch of sort of standard manipulations that people who work in this field do, right? So you can read the paper, right? The answer pops out that you should do greedy assignment on the enhanced channel, right? And the greedy assignment is precisely the greedy assignment of the achievability scheme, and yields the weighted sum rate because the levels on which you enhance the channel for receiver 1, you always assign those bits to receiver 2. You never give them to receiver 1. So this kind of pops out of writing this optimization problem when you go to solve it.
So is this transformation always possible? Like you can always transform the channel the enhancement into a degraded. The channel enhancement always.
For this layered erasure broadcast channel, yeah.
All cases. There's no case where.
No, it's as long as you but this enhancement idea appears. It's exactly the same idea as in the Gaussian vector broadcast channel, but here it's in a much simpler form. The thing is, what you can't do is, no one has figured out some general way to do enhancement of a broadcast channel to always do this. Right? This is a method that seems to work for some subset of broadcast channel problems. And I guess over time it's an expanding subset.
So this is possible because you started out with this deterministic model.
Oh, is it possible? Well, yeah. Okay. So every paper you have some surprising thing happen that's good, right? And it's possible in this case, right? It wasn't so obvious that it was possible to do this.
But I don't know, maybe you can look at the data as a minor.
Maybe. I mean, but there, right, they do, essentially they do some, they use generalized eigenvalues to sort of create, in some casual way they create, parallel channels that are either degraded or reversely degraded. So it's different, but related in some way.
So now can you go back to this vector broadcast channel?
Yeah, we'll go back. So I'm trying to move along, so we only have 15 minutes left to do the other half of the talk. Well, maybe you started 10 minutes late. Okay, so here's how the system works if you think about it, right? You have two users, and they both have bit stream, and basically you assign some encoders to receiver 2, some encoders to transmitter 2, some encoders to transmitter 1. And the way I think of using this channel is that, in fact, right, each of these is an erasure channel. And if you were to actually have a layered erasure system, you would take the levels and in each level do an erasure code, independent of the other levels, and users would just stream bits to those things, and that would achieve capacity. So let's go back to what we care about, the AWGN real channel. And so, the idea here is that maybe now we get some insight into this channel. So here we have fading state distributions given by these NIs. Here we have fading state distributions given by the complementary CDFs of the channel name SI, right? Here we have bit outputs, and here we have Gaussian outputs at any particular instance, right, given the channel state. So,
Excuse me, right, but here the correlations get really trickier, because on the left-hand side for your binary erasure channel, essentially when you're saying if you miss bit number n, then automatically all the bits below are already. So here you are now into the sole decision domain.
So the answer is sort of, this is a kind of a, it provides an insight as to how you might do things, but you know, you have to do all of the theorems and the math. You have a do-over, right?
Okay.
It's just kind of
all the likelihood ratios again.
yeah, you can't directly translate any of that. So but there are two messages, right? In Achievability, you use this kind of layered independent signaling, and in the outer bound, you enhance the channel for receiver one, the less favored guy, to create a degraded broadcast channel. So we can try those ideas over here and see how they work as ideas. Okay, so let me see which one. I think okay, so we're going to do the outer bound first, right? The outer bound, we do almost exactly the same enhancement. We take the channel gain for receiver one and convert S1 to S1 with a little tilde on it, right? And what we do is we create a new complementary CDF, which is the maximum of the old one and the weighted old one for the other guy. And maybe if this number is bigger than 1, then you make this be 1 and be happy. And you can verify that's a valid complementary CDF. And you can verify now that S1 tilde is stochastically bigger than S1, and you have a degraded channel. And now you write down the weighted sum rate optimization for the degraded channel. And you essentially turn the same crank mostly. Right? You now have to solve this problem. Okay, so here, this is my proudest moment in Beamer. You'll see that, like, I'm gonna have a proof where, like, next box 1 scrolls off the screen and box 2 moves up. It's quite an accomplishment for me. So we form the weighted sub-rate optimization, and then we do a bunch of mechanical stuff that involves, you can find sort of a generic channel state output when the state is S, call it YS. It's the typical output of the Gaussian channel when the SNR is S.
The channel state S is a continuous state.
So this is just a number, right? And this little s, yeah, it's continuous. And but then for capital S, which is a random variable, this thing is the ergodic capacity of this, right? Which is an integral expression. Okay, so you form your weighted sum rate optimization, and you do a bunch of stuff involving rearranging entropies and replacing expressions for y1 and y2 with integrals that involve this generic thing, and eventually you get this expression, right? And it's kind of exactly similar to something you got in the layered erasure channel, which is a weighting term that depends on the enhanced complementary CDF, the difference in that and the weighted one for user 2, and then something here that involves information and entropies, right? So what this term I prime actually is it's the derivative of the mutual information between the input X and this generic output YS when the SNR is S, given this side information P.
The derivative in which variable?
Huh?
Derivative in which variable is
in S.
over S.
Yeah. So there was kind of an integration by parts here to get this into I prime instead of I, right? So then we, recent results in the literature make this kind of very tractable, right? Because this derivative of mutual information, fortunately by Dunning and Shlomo and Sergio, they found out that this is equal to essentially the MMSE, right? The mean squared error of the estimator of X given this observation YS, right? an SNRS, and given the V to this message. So, yeah.
Suddenly you got this V in.
So V was always here.
V was like, so the same.
V is always the information signal
Yeah,
for
but S
the
is
common.
not, S is what, S1 and S2, or what is S?
No, S is a generic receiver that observes the channel at state S. So what happens here, okay, if you go back, right, is we did some work, right, in going from this, right, where you have to break this up and write it as conditioned on S1 and S2 and blah, 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 and you have integrals, right? And then you express those integrals in a generic notation S, and then you do some integration by parts, and you get here. It's kind of standard stuff, but, so I'll make one remark, which is you can also get to this answer by not using the MMSE, by doing an entropy power inequality. But this is kind of nicer. All right. So where are we? Okay, so you replace that in your expression. That's nice. And then now what you want to do is you want to choose the V to maximize this thing, because you want to find an outer bound. Right? So you have to say, well, there's some V that makes this as large as possible. So there's only two things you know about this MMSE, right? It can be as small as 0, and it can be as big as 1 over 1 plus s. So what you do is, to get an outer bound, is whenever this term is positive, you make this be the maximum. You replace it with the maximum. And whenever this term is negative, you replace this with 0, and you get an outer bound. And essentially what this is saying is that you would really like to, at different SNRs, assign bits to different users, right? So essentially at some SNRs, when this thing is 0, right? You are saying that there's no uncertainty in the X given the channel state at given B, and that really corresponds to assigning the bit to user 2. In some, I can't say really assigning because we don't really have any bits in this outer bound. We just have a rate region. Yeah.
Is it a weird incarnation of water filling in some way?
I would say no, because there is no, well, okay, so is omega really a Lagrange multiplier?
Well, maybe it's possible to find a formulation where it becomes one, because the other one,
Yeah,
it's like
maybe.
positive and negative, it kind of exactly like raise over the level of water.
So here was what I was trying to say, is that this V specifies the fading state level for which receiver 2 is the max speed. Right? And so the thing is, a V that actually achieves this seems physically unrealizable, right? But you get an outer bound. That's good. And when you evaluate that, you find out all this integral breaks up, and you get the same greedy assignment of channel states you had in the layered erasure case, which is channel states S, where the probability that the SNR is bigger than S for receiver 1 outweighs the weighted version for receiver 2. You think of those levels S as assigned to receiver 1, and the others assigned to receiver 2. So, and then you get these outer bound rates that look like this, which maybe they make sense to you or not. And if they don't make sense, here's the interpretation. If you just think about rewriting ergodic capacity, ergodic capacity of this channel, right, is this integral, 0 to infinity, complementary CDF, 1 over 1 plus SDS. That is ergodic capacity. And so when you look at this pair of integrals, what you see is that for each little smidgen ds of channel state, you're assigning it to one of the two guys and getting a contribution to ergodic capacity equal to the ergodic capacity you get when you assign it to the person. So if I1 was the whole set and I2 was nothing, you get ergodic capacity here for receiver 1. And conversely, if you assign everything to the other guy, you get ergodic capacity for receiver 2, and what this outer bound is kind of doing is partitioning the ergodic capacity by channels. So, okay, so that's the outer bound, and you figure it's weak because we use an outer bound for which we don't know a signaling scheme that can achieve that MMSE property. Okay, so the achievability. Okay, so this is what Leo's point is. How do you do it?
So wait, but I didn't get this right because it sounded to me like you went from the ergodic capacity of a single link to a time multiplex of two ergodic capacities.
And remember, the thing is, it's just an outer bound. It's not necessarily achievable. Like,
right.
It's just you do
But that's
a lot of math.
You have to do worse than that. There's no way to
You
do
can't do
better.
better than that, no
Right.
matter what you do.
That
And the
makes
question is, can you get close to that?
Right.
That's the
Okay.
question. So maybe if you're thinking about achievability, the classic candidate scheme was do some kind of Gaussian superposition, right? So that's what the solution was in the Gaussian channel with fixed SNR. And the idea is maybe you can decode layer n after stripping off the first n-1 layers. On the other hand, the problem with that was to decode layer n, you better be able to decode the prior layers, the higher bit layers, and this fact has kept people from proving this is capacity, and it turns out it's not capacity. An alternate scheme, maybe you could do some kind of dirty paper coding. At Allerton last year, I gave a talk saying that this has some really good properties. And then after I gave my talk, I found the bug in what we were doing, and it turned out it's not so good. So I'm not going to talk about it, but somehow it's in there. And I spent 2 or 3 months, you get a pretty good result, and then you find some mathematical problem, and you think, no, this is just very minor. This is the way it should work. So you spend 2 months trying to fix the math, right? All right. So let's not talk about it. So here's the scheme we actually use, which is essentially something Leo just proposed 45 minutes ago. All right, we're going to do a binary superposition. So you can construct a signal x of t, which is like it's bits. These are plus minus 1 bits, xn, and each bit at level n is weighted by 2 to the minus n. Right, and then this root 3 out front is just a scaling factor to give this thing unit power. So that's the binary expansion scheme, and then the idea is we'll use that kind of encoding structure that we had. It's almost the same picture here for layered erasure, where we'll think about some levels being assigned to receiver 1 and other levels being assigned to receiver 2, and we'll do an independent encoder on each of these levels. Right? But it won't be an erasure encoder, it'll be something else. And so the key thing to notice here is that here we have an index of time, right? And the reason is that we're going to, when we feed these bits to encoder 1, right, he's going to in time construct a long code word. Right? So the marginal property, though, each symbol there is plus or minus 1, I put probably, but in fact, right, you get a code word in time that will be used for decoding. But at each instant in time, these signals are combined by this combiner in this way, and you just transmit this x of t in time.
So is it equivalent to say you have an infinite layered erasure?
We have an infinite binary superposition. So let's be really clear. Suppose we don't do an infinite number of these layers, we just do 2. So you have n equals 1 to 2, xn, 2 to the minus n, right? That gives you 4 possible x's, like at 3/4, 1/4, minus a fourth, and minus 3/4. If I put it in the root 3, I think got left out of there. Stretch it out to make it power 1. It wouldn't be root 3, it'd be some other constant a little bigger. Yeah.
Just two observations. These bits, first, they actually correlated now with each other, and secondly,
Oh,
they're
not
not.
necessarily. Who says they're correlated?
Oh, sure, and they're not, well, if you add AWGN, you will see that they're not equally protected, and for example.
Oh, they're not equally protected, that's true, yeah. But,
You know that
it's not so clear that they're correlated.
do something wrong, that two side 0 or 1.
Huh?
You can do something right, that two side.
I could, but there's a reason I didn't. Because really 0 is -1. And actually, if you go read the paper, there's some nice reason to not do it randomly, or to not do it with some gray encoding.
Similar to the PICF.
You know, Rohit, I'm sure you're right, but
So what's wrong with the gray code here?
well, so it's not a gray code.
Well,
because
it is definitely not, but I mean.
This has, so let me go into some properties here. So technically, right, we do this, we're only talking about the I channel, but we do it on I and Q, right? So if you just do 2 levels on I and Q, you're really doing a 16 QAM. And, you know, and in the general case, you're doing, you know, 2 to the infinity QAM, right? That this thing becomes, if I do one more level, right, we get all the bits in between, right? Plus and minus, and it gets denser and denser until it becomes a dense brick, where really what you're doing is signaling with uniform random variables, right? So really it's this incredibly dense QAM, is the signaling scheme. So for the bit detection, here we combine this and we send this signal and we amplify it with something and add a noise. Now we get a Y of T. All right, and then we'll do some normalization here where we know the channel states. We'll rearrange it as the Y is now this binary expansion plus a noise term that varies with the channel state. So you put the vary the receiver noise in. And so then what we're going to do is do something kind of stupid, which is at each point Y of T, we're just going to make hard decisions on the bits, right? And the hard decisions are like, oh, Y of T is equal to this binary expansion, right, plus a noise term. We're going to guess that the binary expansion of Y is these XNs. So we guess that X hat n is just Y, the nth bit of the binary expansion of Y.
So you do the estimation in one shot, or you do consecutive? Like
No,
first
so we do bit detection, symbol by symbol. And then we're going to create, so sometimes bits at a level are wrong or not, right? So we're going to create essentially a binary symmetric channel at each level, and then do an encoder.
Are you assuming that binary symmetric channel is IIT?
Well, it is IIT.
So because here actually the more kind of natural, at least kind of without giving many thoughts to it, I would rather decode this in a sequence. Like first decode the most significant bit, which has
okay.
most energy, and
I
then
have a
subtract
surprise
it.
for you. You'll be
And then subtract it and keep going.
That's sort of what you think, but we're going to do the opposite.
Oh.
Okay, so here's the thing, right? If you want to evaluate, well, how good is this at level N, right? Probability that the nth bit is detected properly, right? It's bounded below by the probability you detect all the first n bits correctly, right? Because sometimes you can have these bits be wrong and you could guess this right? But certainly lower bounded than that. And then there's kind of a nice homework problem that says, oh, if you know what the first n bits of the input are and know the channel state, the situation you have is this, is that given these, that the output Y is those first n bits, which is this is the binary extension of it, plus a thing that's like an interference term from all the less significant bits, which we call LSB interference, plus the Gaussian noise. So now you're doing detection on, oh, you'd like to know this thing perfectly, you'd like to detect it, where you're subject to a thing here which is actually has a uniform distribution, right? It's a scaled uniform plus a thing with a Gaussian. And there's a homework problem in detecting if you're you know, with an interference at the sum of a uniform and a Gaussian that are independent. So you can solve that homework problem, and you can show that your channel at level n, right? You can write it as a kind of a binary symmetric channel, is where the error probability is bounded by this expression that is the solution to this homework problem. And if you sort of dig into it and go in the paper, you'll find, oh, what this expression says is that, like, this BSC becomes useful when S is bigger than 2 to the 2n, which is kind of exactly what you have in the layered erasure case. Kind of like, well, every 6 dB, you get another 2 bits. Okay, so now we'll sort of switch to looking at the complex channel, and now at layer I, right, you get a rate, which is 1 minus the entropy h of the crossover probability, and you take an expected value of that for ergodic capacity, because each bit will have the average of this capacity over time is in fact the ergodic capacity of that layer I channel. And then you multiply it by 2 because we're now going to do the I and the Q together. You get this lower bound on what rate you can get, and you add these all up, and so you get a theorem that says, well, I'll partition the channel in some way where some bits I'll assign to user 1 and some to user 2, and depending on the partition, I have a very quick call I have to take. I guess not. So we can get all manner of rate pairs that look like this depending on how we divide the bits up. So the question is, well, okay, so is that any good? Okay, so the question is, when we try to say is it any good, we have to have some way of deciding how are we going to assign the bits. So the assignment we'll use is the assignment that mimics the assignment for the layered erasure, right? And mimics the assignment of the outer bound. So imagine like this is the complementary CDF for user 1. Here is the complementary CDF for user 2, weighted by omega, which happens to be 1, right? And so what we'll do is when the blue line's above the red line, we'll assign bit levels to receiver 1, and this is the channel quantized in essentially dB steps. So in this example, you know, up to this crossover, you assign these levels to receiver 1 and these levels to receiver 2. And if omega gets a little bigger, the complementary, this weighted complementary CDF moves up for receiver 2. Now we just assign some middle range of bits to receiver 1, and we assign the more significant bits and the less significant bits to receiver 2. So we use this kind of idea, and so looking at this example, right? Receiver 1 decodes, and you know, with this idea we could calculate those rates I had before. But look at this example. Receiver 1, it decodes x4 to x9. Receiver 2 decodes x1, x2, x3, and x10 through whatever. So the observation here is that, you know, if you use the formulas we had earlier, right, this homework problem, the coding xn is always subject to the LSB interference from all those less significant bits, right? But when you do this thing where you assign the bits in different ways, you can actually do an additional kind of a stripping, right? So we do something called reverse stripping, and so the idea in reverse stripping is that, for instance, in this example, right, receiver 1, right, this bit number 9, he has to decode in the presence of this LSB interference because these bits are assigned to user 2, and he may or may not, they may be at code rates that he can't decode, right? But once you build a coder for the bit at level 9, right, you build it at such a rate that handles this interference, right? Then when receiver 1 goes to decode bit 8, right, in fact, he can strip this bit number 9. You can say, oh, well, I will wait till for a whole code word to be transmitted. I will do some really reliable decoding on bit 9. I will now strip the bit 9 signal, right? And so bit 8 sees LSB interference not starting at bit 9, but instead at bit 10. So it effectively reduced the LSB interference by, I think, 6 dB. The 3 and 6 dB is kind of confused. So the result is you get this enhancement effect that, and now bit 7, right? He's going to strip both bit 8 and bit 9, and he'll see his LSB interference 2 levels down, right? So there's something kind of strange here.
So the encoders
You know,
are
it is similar to successive inference cancellation.
Yeah, but it's the opposite.
No, but it's.
Yeah, because the reason it's the opposite, right, is because the signals for receiver 1, right, bit 4 is the most powerful signal for him, right? But in fact, he strips the weakest one first. He decodes and strips the weakest and successively decodes stronger ones, whereas all other stripping superposition encoding techniques always first you decode the strongest in the presence of the weaker ones, and then you strip.
But if you look at the corner point in the polymetroid, you're actually doing the opposite, right? You're actually giving the best trade to the guy by stripping everybody else first. So it's the successive inference cancellation in the polymetroid is always different from the way we did it in communications.
Yeah, okay.
This
So
is
maybe it is more like that.
This is like that. Okay.
Since I brought that up, but they're basically saying that the channel 1, where you know the channel you know well, you can subtract those off, right?
No, it's a
Instead
question of
of
knowing.
inside the
No,
constellation, you
it's
really understand it.
no, it has to do with that the bits that are assigned to receiver 1, right, are specifically encoded at rates that guarantees he can decode them, right? And so you encode them, and what you can do is, because they're assigned to receiver 1, you can design them to be encoded at rates that can be reliably decoded and stripped. Whereas the bits for the other guy are encoded at rates that are compatible for him, and you just have to tolerate that.
So the receiver 1 bits look like noise, they're at too high a rate.
To receiver 2.
Right.
Yeah.
And you
generally.
subtract them off as best you can, but they're.
No, you don't even assume you subtract them off, you just tolerate them. When
He's
other
already
guys-
sitting with a noisy channel, so they don't make much of a difference.
Well, there's always some difference. It could be.
That's the tangent coming off.
I guess the difference comes from the model, because in the general model, it's like 2 sources add up together, but here it's like layered erasure. So there's no cross interference if the noise is absent. So think about the layered erasure model at gaming. When noise is absent, actually there's no cross interference. But here it's like if noise kicks in, there should be some ambiguity.
But you know, it's really, yeah, that's true. Right. So I'll move on. For this scheme, you can analyze both the outer bound. You know, if you make up any particular examples of channels, you can analyze the outer bound. You can analyze the inner bound with this reverse stripping. You can analyze the inner bound without the reverse stripping. And then for some cases, like for instance, if you just have fixed SNR AWGN channels, you can say what capacity is and analyze the value of that. So the good example is B on the right, where the SNRs are high, right? You receiver 1 is 50 dB after SNR, right? Good high SNR. Receiver 2 is not nearly as good, only 20 dB, right? And this green curve is the capacity, because it is the graded broadcast channel. You know the capacity. It's superposition coding. The outer bound is this blue curve outside of that, right, which has lost something because of this upper bound for the MMSE. Right? Below that, if we do our achievability scheme with the reverse stripping and the bit assignment, we get this red box curve, which is like a sort of about a bit away. 7 is here, 6 is there.
So S is 1 here.
Huh?
The channel state S is always 1 here. The ZWG.
So actually, no, S is the number that gives you. S1 is such that it's the 50 dB, right? And S2 is 20 dB. If the SNRs are worse, you get sort of qualitatively the same thing, and still you're down about a bit, but 3.5 to 2.5, that 1 bit seems like a much bigger deal, right? Compared to 6 point something to 6.
But S does not have a distribution.
Huh?
S does not have a distribution.
It has a PMF that's a 1 about, right? So, and of course the reverse stripping looks like it's worth like about 2 bits, right? So, several bits. All right, so here's another example, which is kind of a better example. Here we have what we call an intermittent AWGN channel. It's each receiver either gets nothing, S is 0, or it gets a really good signal with some channel state, some probability. So receiver 1 gets 20 dB with probability 1/2, or it gets nothing, or receiver 2 gets 10 dB with so receiver 2 is AWGN. He always gets 10 dB, or in the second example, he always gets 20 dB. Receiver 1 is intermittent. Sometimes he gets a good signal, sometimes he gets nothing. So the highest in our example is still on the right. And now here we don't know what the capacity of this channel is. Outer bound is sort of the same form as before. It always looks like this because there's some corner point where you start changing the rate, the assignment. Once again, sort of the reverse stripping scheme is about a bit away, and without reverse stripping, you're several bits away, maybe 3 or 4. All right, so the problem is that I can make similar curves with Rayleigh fading, and kind of they always have this character of a bit or so. You could ask this question, well, is it just that are these schemes pretty good, just for the examples you came up with? But like, can you somehow assert that they're always pretty good? So sort of the goal in using this kind of deterministic channel approximation is that it should motivate a fading channel scheme that is within a constant gap of the true capacity. So we spent a lot of time working on constant gap results, and what we're able to show is that we're always within a terrible gap. But I think the problem is the analysis of the gap, not the actual schemes. So in the gap analysis, we didn't have any way to incorporate this idea of reverse stripping, because reverse stripping is something that how it gets implemented depends on the specific instances of these channel state distributions, right? And when you try to do a constant gap analysis, you want the analysis that applies to all channel state distributions. You can't use the specific properties of the distribution. So in doing the constant gap, we assumed that we didn't use reverse stripping. So we're looking at performance for specific channels that looks like this or like this. There's kind of an observed kind of 2-bit penalty. Use the ability to use reverse stripping in the gap analysis. There's another bit of loss in this gap analysis is that if you read the paper, we had to do a kind of a channel state quantization. So because the achievability scheme really works on these specific levels, right? We had to do something where we quantize the channel states for the outer bound to be always sort of the best state in the 6 dB range, right? Probabilities. And the inner bound, we had to give it just the worst assumption. And the result was we sort of did a 6 dB gap in the channel states of the inner and outer bound in their distributions, and there's kind of like a 2-bit loss in there. And I think there is probably 1 bit in the binary expansion superposition, and I think there's about, based on what we saw in those examples, 1 bit in the looseness of the outer bound at some points. So I think that this outer bound, in some ways, it's conceptually nice. It says even if the SNR is very, very high, you are within a constant gap, right? It's not like, oh, in some asymptotic regime that this scheme falls apart. If you really have a channel that transmits a lot of bits, the scheme will resolve a lot of bits. But in fact, the actual bound we get, I think, and I encourage people to read the paper and improve it. I think the bound could be a lot better than the 6.3. So I think I'm all done, and I appreciate your patience. I realize this is kind of a technical